A balanced modulator is an electronic circuit that mixes two signals, typically an audio signal and a high-frequency radio carrier, to produce a double sideband suppressed carrier signal. In standard amplitude modulation, a massive amount of transmitter power is wasted broadcasting the carrier wave, which contains no actual information. A balanced modulator solves this by mathematically multiplying the two signals and cancelling out the carrier, leaving only the information carrying sidebands. A balanced modulator takes two inputs. One, the modulating signal, the information you want to transmit, like a voice audio wave. Two, the carrier signal, a continuous high-frequency radio wave generated by an oscillator. The circuit is designed with a symmetrical, that is balanced layout using non-linear components like diodes or transistors. When the carrier is fed into this symmetrical bridge, it is split into two equal but opposite currents that cancel each other out at the output transformer. Because the carrier is suppressed, the output consists entirely of the sum and difference of the two input frequencies. Upper sideband is carrier frequency plus modulating frequency. Lower sideband, carrier frequency minus modulating frequency. The balanced modulator is the critical first step in modern voice radio communications, specifically in generating single sideband signals. Because the balanced modulator has already eliminated the carrier, a transmitter only needs to pass the resulting double sideband suppressed carrier signal through a highly selective band pass filter like a quartz crystal ladder filter. The filter strips away one of the sidebands, leaving a pure, highly efficient single sideband signal to be amplified and transmitted. Common circuit designs. Diode ring mixer, the most classic and robust design, using 4 matched diodes arranged in a ring and 2 center tapped transformers. It is passive, bidirectional, and handles wide dynamic ranges well. Active integrated circuit mixers. Integrated circuits like the NE602, SA612, or MC1496 use internal cross-coupled differential amplifiers, a Gilbert cell, to achieve modulation with fewer external components while also providing signal gain. FET transistor modulators, using matched field effect transistors or bipolar transistors to actively switch the carrier on and off at the audio rate. A little more detail about diode ring mixer, which is the commonest in usual homebrew circuits. A diode ring mixer, often called a double balanced mixer, is a purely passive circuit that mathematically multiplies two signals. It is the workhorse of radio frequency design because it inherently suppresses both the original carrier wave and the modulated audio, leaving only the desired sidebands. The classic diode ring mixer consists of only 3 components: input transformer T1, an RF transformer with a center tapped secondary winding, output transformer T2, an RF transformer with a center tapped primary winding. A diode ring, 4 identically matched diodes, usually Schottky diodes for fast switching, connected in a continuous circle, anode to cathode, all the way around. The carrier signal is injected into the primary winding of T1. The modulating audio is applied between the center tap of T1 and the center tap of T2. Output signal, that is the double sideband suppressed carrier, is taken from the secondary winding of T2. Unlike standard amplifiers where signals remain analog and linear, the carrier signal in a diode ring mixer is fed at a very high power level. Its job is not to be amplified, but to act as an aggressive electronic switch. Because the carrier is so strong, it rapidly slams the diodes into one of two states, fully conducting on or fully blocking off. On the positive half cycle of the carrier, two diodes on one side of the ring are forced on, while the other two are reverse biased off. On the negative half cycle, the first two diodes turn off and the opposite two turn on. Carrier suppression relies entirely on perfect physical and electrical symmetry. When the high power carrier wave turns the diodes on, here is why it never makes it to the output. 1. Current splitting. During a positive half cycle, the carrier voltage at the T1 secondary pushes through the two forward biased diodes. 2. Opposing magnetic fields. This current enters the top and bottom of the T2 primary winding simultaneously and flows inward toward the T2 center tap. Phase cancellation. Because the current is flowing through the top half of the winding in one direction and through the bottom half in the exact opposite direction, the two resulting magnetic fields collide in the transformer core. The null. Equal and opposite magnetic fields perfectly cancel each other out. Because there is no net changing magnetic field in the core, zero voltage is induced in the T2 secondary winding. The carrier essentially traps and destroys its own energy within the primary side of the output transformer. This happens on the negative half cycle as well, just through the other two diodes. If the carrier cancels itself out, how does the audio signal get transmitted? The modulating audio signal is injected across the center taps of the two transformers. Because it enters at the center taps, it is unaffected by this phase cancellation that destroys the carrier. However, the audio signal must pass through the diode ring to get from T1 to T2. During the positive half cycle of the carrier, the active diodes route the audio signal through the output transformer in a positive polarity. During the negative half cycle of the carrier, the other set of diodes route the audio signal through the output transformer in a negative polarity. However, the audio signal must pass through the diode ring to get from T1 to T2. During the positive half cycle of the carrier, the active diodes route the audio signal through the output transformer in a positive polarity. During the negative half cycle of the carrier, the other set of diodes route the audio signal through the output transformer in a negative polarity.